Classwork 2-4. We are going to now look at multiplication with roots. And we're going to start off with number 1. What I want you to see with number 1 is you know that side-by-side parentheses means multiplication. You also know that the 2 and the square root of 11 are being multiplied. And then in the next parentheses, the -7 is also multiplying, and the root 3 is also multiplying. So we've got really multiplication of 4 different things. We are able to squish together the numbers that are outside the square root and actually multiply them. So 2 times -7 gives you -14. And then for the square roots, you want to remember that there's an exponent rule. And roots are the opposite operation as exponents. Exponents distribute over multiplication. Therefore, roots distribute over multiplication, and they also undistribute. If you have multiplication between 2 roots, provided it's the same index, and in this case, it's an understood 2 index. As long as those are the same index, and I'm not going to give you anything different than that, then you can use the exponent rule of the multiplication comes under the square root together. And I want to make sure to emphasize you cannot do the combination if they're adding. If this was the square root of 11 plus the square root of 3, you could not do this. This is incorrect. Make sure that you don't allow addition to go through the distributive property with roots. So then this simplifies to -14 times the square root of 33. And you should double check to see if the number you get here can be simplified further. And simplified further would be if it's divisible by a perfect square number that can be also taken out of the root. So if you break 33 down, you can see that 3 times 11 is 33. 3 is a prime number. 11 is a prime number. There is no perfect square number that will divide 33. So that is done. Now let's move on to number 2. Just like with number 1, I can take the numbers that are not under the root and multiply them together. 2 times 5 gives me 10. Then I have 2 fourth roots. They are the same exact index root. That means I am allowed to distribute, or in this case, undistribute the multiplication to be under that root to get 21 under the fourth root. And the only way that the fourth root is going to simplify anymore is if you can actually have a factor of a number that shows up multiplying by itself 4 times, and that's not our situation at all. So that is done. And then number 3, again, if it's not inside the root, you can multiply together. 5 times 6. If it is under the same index, both are 3 indexes, then you can go ahead and multiply. 9 times 2 is 18. If there are any factors of 18 that happen to be perfect cubes, you can get that pulled out as well to simplify. But We don't have that. So that is done. Now, that was when you're dealing with square root expressions that are already multiplication to begin with. But now we need to take a look at multiplying square root expressions where you have addition or subtraction involved while you are doing the multiplication. So I want to emphasize first that when you are squaring something that has addition or subtraction, be very careful. An exponent will not distribute over addition subtraction. You need to write out the two parentheses. And then realize that you have to do a big distributive property. Most people will make fewer mistakes if they do the box multiplication. So I'm going to recommend that you do the box multiplication. And a reminder on how to do that. So I take one of them is root 3 minus root 6. The other one is root 3 minus root 6. And hopefully this is looking familiar. For the box I'm currently starring, that box is found by multiplying the root 3 and the root 3. And you don't have to write all these steps, but I want to make sure that no one falls behind in what we're doing, so I'm writing it out. Now, some of you look at that and you know the answer. Some of you don't. If you don't see it, then let me start here. You are allowed to undistribute the multiplication of two square roots and multiply them together under the square root. The square root of 9 is 3. And then take notice that when you multiply the same square root, you're really looking at you're square rooting something that is being squared. So you get just what is under that root when you're multiplying two of the same root. But understand the math going on. Don't just memorize that. I'm going to erase the star that I drew so that I can star the next box. So the box that I've starred now, I am going to multiply root 3 and negative root 6 to get what is in this box. The negative sign is outside of the square root, so I keep it outside the square root. And like we did in the first three problems, I am allowed to multiply the 3 and the 6 together underneath the square root because I am allowed to distribute exponent roots over multiplication and division because exponents are repeated multiplication. Now, this particular square root can be simplified further. Maybe you multiply the 6 and the 3 and get 18, but do you notice what you have there? Or you can break it down further instead of multiplying the 6 and the 3 and see that you have a couple inside a square root, and a couple inside the square root goes through the process of being square rooted and they unite to become just only one of them comes out. Square root of 3 squared is just 3. I'm going to erase that star. And then I'm going to star this box. For this box, I am multiplying negative root 6 with root 3, but then, oh wait, hey, I just did that. So save your time. It is exactly the same thing you just did. So you're going to find it easiest if you just write down what you already found. And then we have one more box. I'm erasing the star. And now this is the box we're working on. I am multiplying negative root 6 times negative root 6. Negative times negative gives me positive. And then do you see what the square root of 6 times the square root of 6 is? And you end up getting just 6. When you do the box multiplication, after you do the individual multiplications, you take all of the results and you add them together. So I'm going to add 3 minus 3 root 2 minus another 3 root 2 plus 6. And I can add my like terms together. 3 plus 6 gives me 9. And then I have root 2's. If it's the same square root, I can combine and smush that into 1. I have negative 3 root 2's minus 3 more root 2's makes negative 6 root 2's. And then you're done. So I want to repeat, anytime you have addition, subtraction in a parentheses, when you're multiplying, you need to do the box multiplication. And look really carefully at 4 and 5 as they are written and see the need for the box multiplication. And for those of you who are very, very algebra minded, let me show you this aspect. Anytime you have multiplication over a parentheses, you're actually distributing one of them over the other. So you can look at this as I have to take this 2 and multiply it over the parentheses and then continue distributing this and multiply that over the parentheses. And then that creates 2 distributive properties. For some of you, you might see this better than the box multiplication, but the majority of people see the box multiplication better. And so that's why that's been the push as to how to go about multiplying when you have addition subtraction. So I'm going to go ahead and get the box multiplication started. It doesn't matter which one you put on the top and which you put on the left. Does not matter at all. So I'm just going to put 2 plus root 3 and 7 minus 2 root 5. And I just realized that with all that work over there, I'm going to erase the work on the previous problem for the sake of it not mixing up here and confusing you, just visually not confusing you. That helps. I've been having this problem lately. Okay. And that's what happens every time. And it didn't save whatever it was that I just did, because it just decided I didn't feel my internet power for a little while. So good night, goodbye, I'll see you later. Okay, I'm back now. Okay. So I didn't finish 7 minus... No, please don't do this to me. Are you going to be this way? Because we're not going to work out if you're going to be this way. I'm giving it a moment because it's going to come back, and now I'm seeing that I have a problem that I'm going to have to deal with. It's not coming back. That's fantastic. Okay. I think I need to have my computer looked at this weekend. All right. So I'm going to star the box. 7 times... Yep, I'm done with you. Okay. I'm going to have to open up another program, so you're going to have to hold on a moment. Oh my gosh. Okay, so that was classwork 2-4. I'm going to one at a time copy and paste over here. Maybe some of you have already finished this problem. Okay, luckily there are other programs I can use. All right. First box, 7 times 2, 14. Second box, 7 times root 3. They can't combine in any way. Third box, I have negative 2 root 5 times another 2. So I can multiply the numbers that are not under a square root together and combine them. And then fourth box, I have negative 2 root 5 times root 3. The negative 2 doesn't have anything to multiply with because it's the only one outside the root. The 5 and the 3 are both under the same indexed root. So I can multiply under the square root. 5 times 3 is 15. And then a final step is to add them all together. So I have 14 plus 7 root 3 minus 4 root 5 minus 2 root 15. Now, the big question is, can you simplify any further? This does not have a square root. Everybody else does. This term has a square root of 3. Nobody else does. Root 5, nobody else does. Root 15, nobody else does. So I cannot add any terms together from there, and this is it. And I'm going to grab, where did I have it? I'm going to move this out of your way so you can finish copying that. And I'm going to screenshot my next problem. Okay, hopefully you've had enough time to write that down. And this is the very beginning of the next batch of classwork problems. These are very, very important. This is going to prep us for Monday's work. And there's a number 6 and a number 7. Both number 6 and 7 are going to use this. So I am now going to screenshot number 6, bring it over here. And here we go. I have this number 6 set up so that you actually have the answer column. You're starting with the answer column. You know what to do to a graph if the 2 is multiplied outside of the h. So let me show you what you do know already. If I told you 2 times h of x with the 2 multiplied outside, you stretch the graph 2 units. All the y values are multiplied by 2. But for this problem that we have, the 2 is multiplying to the x before the function takes place. So what I want you to realize is to get this column for h of x, these are what have to go in it. 2x is what is going into my h function. However, whatever is going into the function to make this table for h's, these are what have to go in. So that means that to get -1 for h of x, -2 has to be the one that goes in. To get 0 for h of x, -1 has to be the number that goes in. And then continuing, I just need to basically bring this whole column down. 0, 1, 2, 3, 4. And now, if I can get this to do what I want it to do, I want you to zoom. Thank you. Now, without looking at the other graph, look at the column we just filled in was for 2 times x. Can you figure out what the x column needs to be if those are the values of 2 times x? So if 2x is -2, then x has to be -1. If 2x is -1, then x has to be -1/2 or -0.5, your preference, whichever. If 2x is 0, x is also 0. And hopefully you see that to go from 2x to x, you have to divide by 2. So 1 divided by 2, 2 divided by 2, 3 divided by 2, and 4 divided by 2. If you're asked to sketch the graph of h of 2x, then you need to plot the following points. -1, -1, and then -1/2, 0, and then plot the point 0, 1, and so on. So let's do that. -1, -1, -1/2, -1, or sorry, I read it wrong. The problem is trying to ignore this middle column can be very difficult. So what I'm going to do is I'm going to do this so that I don't accidentally plot the wrong numbers. Going back. Okay, -1/2 goes with 0. I was trying to plot that point. There we go. Then we have the point 0, 1. Then 1/2, 2. And then we have the point 1, 0. And then we have the point 2, -4. Do you think you know what the graph of h of 2x looks like? Based on the point plotting that we just did. And also looking at the fact that h of x started with 2 straight lines. Do you think you see what happened? And now that I've drawn those 2 lines, and you take a good look at it, what does multiplying the x by 2 do to the original graph? And you can type something in chat if you see it. So again, what?
Narrows it.
Mm-hmm. Right. So before, when the 2 was multiplied outside, it vertically stretched it by 2. But when the 2 is multiplied inside with the x, it squishes it, it narrows it horizontally by 2. If you take the original x coordinates, these original x coordinates that you see on the graph, you need to actually divide them by 2, keep the y values as they are, and that will give you how it squishes. Now, the next problem, and I'm going to take this picture and I'm going to move it. And I'm going to erase it, and then I'm going to take a screenshot of the next problem and bring it over. Okay, and paste. Yes, it pasted what I wanted it to paste. Okay. We're going to do the same thing that we just did with this one. Whatever goes into the h function to give me these values, who goes in needs to be this column. So the x over 2 column, in order to match with the h of x over 2, is going to cause me to bring those x values down here. And after bringing those x values down here, I'm going to focus on just this problem. If x over 2 is equal to negative 2, what is x? And is everyone getting negative 4? And then if negative 1 is equal to x over 2, then what is x? Negative 2. If x over 2 is equal to 0, what is x? Still 0. Do you see what you need to do to everybody in the x over 2 column to get it back over to what is x? Hopefully you're seeing that what you need to do is multiply by 2. So multiply by 2, multiply by 2, multiply by 2, multiply by 2. We're going to now plot these points. The only way I'm going to not mess up in plotting my points is if I get this column to not be seen. And now, if I want to sketch the graph of h of x over 2, given the graph of h, I'm going to plot the points negative 4, negative 1, negative 2, 0, 0, 1, 2, 2, 4, 0, 6, negative 2, and 8, negative 4. And do you think you see what the new graph is? We had 2 lines, and if I'm just doing a stretch compress, then I'm still going to have 2 lines. And now take a good look. Do you see that when x is divided by 2 inside the function, that causes the parent graph to have a horizontal stretch by a multiple of 2? Are you starting to see some interesting patterns? When arithmetic is outside the function, so in the past you have looked at taking h of x, or just some function, and multiplying it by 2. You vertically stretched it 2 units. You took the y values and you multiplied them by 2. But if the operation is inside the function, you see right here that x is being divided by 2. So you need to go to the graph of the original function and take those x coordinates and do the opposite operation than it says. You see divided by 2, so you're going to multiply by 2. And if you take each of these x coordinates and multiply them by 2, you'll see that this is what you get. You don't want to waste your time doing a table like this every single time you go through this process. You want to understand what to do to the graph when you are told about the manipulation and not have to use the table to help you through. You want to get to that point anyway. I want to point something out to you. When we did this horizontal stretch, do you see that the y-intercept did not change? So what is on that y-axis is holding on to it while everybody else is either being stretched horizontally away from it, or in the previous case, squished horizontally toward it. And now I'm going to show you the graph we have horizontally. If I can get it to move. There we go. We have 10 minutes left. So if you look at this horizontal graph, do you see that it held on to its y-intercept? Trying to zoom in a little bit on it. It held on to its y-intercept, and everything else was horizontally squished by dividing all the x's that were there by 2. And perhaps this helps you to start thinking about why is it that, and I'm going to use an example that you're familiar with. If you start off with the graph of y equals x squared, and you see this addition is outside the function, and you translate your graph up 3 units, which means you're adding 3 to the y values. But when you see plus 1 with the x, you're not going in the positive direction 1 unit. You're going in the negative direction 1 unit. You're going left 1. And to do that, you are actually taking your x coordinates and you are subtracting 1. So what is going to be fully presented on Monday is the issue of if you have an operation outside a function that affects the graph's y value with the exact same operation that you see. If you see an operation inside the function that is an operation on the x input variable, that affects a graph with the opposite operation to the x's. And if you can see that as the primary thing going on, it's going to save you a lot of grief and heartache in manipulating parent graphs. So I'm going to now copy paste the last part of the classwork. And bring it over here. And okay. When a transformation is made by multiplying x by a number, the x coordinates of the parent graph are transformed by dividing all of the x's by that number. And the reverse is also true. So that reverse would be if the transformation is made by dividing x by a number, the x coordinates of the parent graph are transformed by multiplying those x's by that number. And this is a really, really valuable thing to grab a hold of. Okay, it's Friday, so I am off on what time we're out of here. Do I still have that? I'm curious, do you guys have to every single Friday look up the bell schedule? It's so bad I've got it on my, well, you can see I've got it on my desktop because I can't remember every single time. Yes, we have 5 more minutes. So I'm really happy I managed to get through all of that in the amount of time. I'm going to